Inside this smartphone are 62 microchips containing a total of 90 billion transistors. These microchips are incredibly powerful and the cornerstone of all technology. But how are billions of nanoscopic transistors manufactured into a microchip the size of a tiny ant? Well, all these microchips were manufactured in a semiconductor fabrication plant like this one. Inside it is a clean room, which spans the area of 8 football fields and is filled with hundreds of machines, ranging in size from that of a van to that of a city bus, and costing anywhere between a few million and $170 million. Within this microchip factory, silicon wafers travel from machine to machine and undergo around 1,000 processes over a 3-month period. And by the end of production, each silicon wafer will be covered in hundreds of CPU chips, each containing 26 billion transistors. When we zoom in, we can see the nanoscopic transistors at the bottom and over a dozen layers of wires above. This integrated circuit is then cut out from the wafer, tested, and packaged so that it can be installed into your desktop computer. In this video, we're going to explore the entire microchip manufacturing process and show you how billions of nanoscopic transistors and an impossibly complex 3D maze of wires are manufactured in one of the world's most technologically advanced microchip factories. It's an incredibly complicated process, so stick around and let's jump right in. A portion of this video is sponsored by Brilliant.org. There are 2 sides to understanding how microchip manufacturing works. The first is the sequence of steps and processes needed to build the nanoscopic transistors and the labyrinth of wires. Whereas the second is how the semiconductor fab and multi-million-dollar equipment of the clean room floor work. And we'll be flipping between these 2 sides to get a complete picture. Let's start by opening up this desktop computer, focusing on the CPU and taking a look at what's inside. Here we have an integrated circuit, or die, which we'll refer to as a chip. This chip has 24 cores, a memory controller, a graphics processor, and many other sections. Within one of the cores, we can see its block diagram and the various elements. Zooming in on this multiply block, we find a layout of 44,000 transistors that physically execute 32-bit multiplication and constitute just 0.00017% of the overall 26 billion transistors in the CPU. Zooming in even further, we see layers of metal wires or interconnects, and at the very bottom are the transistors that form the basic logic gates. Note that these layers of metal interconnects aren't floating, but rather the empty space that you see is filled with insulating materials, thus providing structure and preventing the metal wire layers from touching. Furthermore, here we're only showing the transistors at the bottom and 5 layers of metal interconnects, with vias traveling vertically between the layers. In actuality, there are a total of 17 metal layers of wires in the CPU, and each successive set of levels uses larger and larger interconnects. At the bottom are local interconnects that move data around this 32-bit multiply circuit. In the middle are intermediate interconnects that move data around the core. And at the top are global interconnects that move data around the entire CPU. You might be wondering, how small are these transistors? Zooming in again and past the interconnect layers, we find FinFETs, which are transistors whose channel dimensions are 36 by 6 by 52 nanometers, with a transistor-to-transistor pitch of 57 nanometers. Clearly, the transistors are incredibly small. Here's a mitochondria, a dust particle, and a human hair for size comparisons. Now that you have a sense of what the transistors and labyrinth of metal interconnects look like, let's explore how they're manufactured. We'll begin with an analogy. Imagine baking a cake that's 80 layers tall, with each layer cut to a unique shape. To make this cake, there are 940 steps in the recipe, which takes 3 months to complete and includes hundreds of exotic ingredients. And if any measurement, baking time, or temperature is more than 1% off, then the cake is entirely ruined. That's kind of what it's like to make a microchip. But microchips are even more complicated. Let's look at a single layer of this integrated circuit and run through a simplified set of steps used to build it. To start, a layer of insulating silicon dioxide is deposited on top of the wafer, and then a layer of light-sensitive photoresist is spread across the top. Next, using UV light and a stencil, a pattern is applied to the photoresist. Solvents then are used to remove the areas hit by the UV light, thus creating a patterned mask layer. Using the mask, the revealed silicon dioxide is etched away down to the previous layer. Next, the mask layer is removed, and a layer of